So today we have Ken Mochizuki, and he will talk about various aspects of the non-Hermitian SSH model. So whenever you're ready, you can start, Ken.
Yeah, thank you for the introduction. Can you hear me?
Yes, very well.
Yeah, thank you. Today, I talk about the statistical properties of the non-Hermitian SSH model and symmetry inheritance owing to real spectra. My talk includes not only the results in this specific model, but also general results satisfied in non-Hermitian systems with real spectra. These are collaborators and please read this paper if you are interested in our study. So as you know, the non-Hermitian systems have attracted a lot of attention in various research fields. The scope includes, for example, non-Hermitian topological phases, fundamentals of quantum theory, and effects disorder, and so on. Also, non-Hermitian systems have been extensively studied, not only theoretically, but also experimentally. And various novel phenomena have been observed in many physical settings. Among such various research scopes, in this seminar, I focus on these two notions, that is, disorder effects in non-Hermitian systems and parity time symmetries. These concepts have stimulated the research fields of non-Hermitian systems from about 25 years ago. In 1996, anomalous extended eigenstates were clarified in a non-Hermitian one-dimensional system, which is referred to as Pattern-Nelson models today. In this model, the eigenstates whose eigenvalues are real are localized, but eigenstates with complex eigenvalues are extended. Such anomalous extended states are absent in Hermitian one-dimensional systems. And since this discovery, disordered non-Hermitian systems have been extensively studied. For example, the concept of universality classes in Hermitian systems have been extended to the non-Hermitian systems also. Independently from such studies in non-Hermitian random systems, parity time symmetric systems have also attracted much attention. This is because parity time symmetry or PT-symmetry can make eigenvalues real, although the Hamiltonian is not Hermitian. A sufficient condition for the reality of eigenvalues is that the Hamiltonian and its eigenstates is both PT-symmetric. So the PT-symmetry of the Hamiltonian does not thoroughly make eigenvalues real. And a condition on the eigenstate is also necessary for the reality of eigenvalues. Then in PT-symmetric non-Hermitian systems, the observed phenomena drastically change depending on whether the eigenstates are PT-symmetric or not. So various phenomena have been interpreted or controlled in non-Hermitian PT-symmetric systems based on this feature. Here, since PT symmetry includes a parity operation, which changes x into minus x, then the PT symmetry is fragile in disordered systems. However, in 2004, PT symmetry was generalized to disordered systems in a sense. This is because the notion of pseudo-hermiticity was established in this paper. The pseudo-hermiticity is defined by this relation with a positive definite operator eta. Pseudo-hermiticity is a necessary and sufficient condition for the reality of all eigenvalues. This is contrasted to the PT symmetry, which is a sufficient condition for the reality of eigenvalues. In addition, pseudo-hermiticity, the pseudo-hermiticity operator eta does not include parity operation in general. So pseudo-hermiticity can be satisfied in disordered systems also. Therefore, pseudo-hermiticity can be regarded as a generalization from PT symmetry, focusing on the reality of eigenvalues. While here I slightly changed the topic. While I have focused on PT symmetry and pseudo-hermiticity so far, but there are also many symmetries which are important in both Hermitian and non-Hermitian systems. These are three symmetries which are quite important in Hermitian random systems: time reversal symmetry, particle hole symmetry, and chiral symmetry. These three symmetry relations are defined by these relations with unitary or anti-unitary operators. I explain in the next slide why these symmetries are important. One important feature in non-Hermitian systems is that the kinds of such important symmetries are increased in comparison to Hermitian closed systems. This is because the transpose and complex conjugation is not the same in non-Hermitian systems. For example, regarding time reversal symmetry, we can consider two types of symmetry relations based on original one relation in Hermitian systems. One is the same as the original symmetry relation, but the other is different in that the right-hand side is H dagger, not H. In the same way, we can consider two types of symmetry relations from one symmetry relation in Hermitian systems. So the kinds of symmetries are very large in open non-Hermitian systems in comparison to closed systems. In this seminar, I explore the effects from such increased or ramified symmetries. Before that, let me introduce why these symmetries are quite important in Hermitian systems before entering non-Hermitian systems. At first, the time reversal symmetry and chiral symmetry determines statistical properties of eigenvalues in random Hermitian systems. First, I explain the time reversal symmetry. It is widely known that the random Hermitian matrices are classified into three universality classes. Gaussian orthogonal ensemble, and Gaussian unitary ensemble, and Gaussian symplectic ensemble. These ensembles are discerned by the existence or absence of time reversal symmetry and the value of t square if time reversal symmetry exists. In these symmetry classes, level spacing distribution P of S obeys this functional form. Here, beta takes 1, 2, or 4, depending on universality classes. P of S obeys power law function near S equals 0, and whose exponent is beta. Such universal behavior can be observed as long as the eigenstates of random Hamiltonians are extended, not localized. It is also widely known that in chiral symmetric Hermitian and one-dimensional systems, density of states exhibits peculiar behavior.
Recording in progress.
In chiral symmetric systems, eigenvalues make pairs of plus with opposite signs. Then the eigenvalue E equals 0 becomes a special point in chiral symmetric systems. As a result, then the density of states diverges at this special point E equals 0 in chiral symmetric systems. Such divergent behavior was clarified by Dyson, and this divergence is referred to as Dyson singularity. The functional form of this divergence depends on whether the system satisfies time reversal symmetry or not. From these two examples, that is level spacing distribution and density of states, we can clearly understand that the symmetries of Hermitian Hamiltonians are quite important for the eigenvalue statistics in Hermitian systems. Here, let me summarize the introduction for explicitly stating our objective. First, in Hermitian random systems, the statistical behavior of eigenvalues is determined from time reversal symmetry and chiral symmetry. In Hermitian systems, the kinds of such important symmetries increase in comparison to Hermitian systems. Also, in Hermitian systems, in non-Hermitian systems, eigenvalues can be entirely real, which is related to pseudo-hermiticity. Pseudo-hermiticity can be satisfied in disordered systems also. And then one natural question arises, that is, how statistical properties are affected by such features in disordered non-Hermitian systems. So in this seminar, I tried to answer this question. So in order to explore such properties, I focus on one specific model, non-Hermitian SSH model in this seminar. The non-Hermitian SSH model is a one-dimensional model in which one unit cell includes two sublattices, A and B. Here, the intra-unit cell hopping is described by T1, and inter-unit cell hopping is written as T2. Such hopping terms are described by this Hermitian Hamiltonian H0. There are also imaginary on-site potentials plus I gamma on A and minus I gamma on B. Such imaginary potentials are described by anti-Hermitian term H gamma. Here, this model can describe the dynamics in artificial lattices composed of optical waveguides or dielectric resonator chains with gain and loss. This is not only theoretical model, but can describe realistic materials. In order to study the statistical properties, I consider the situation in which the hopping terms T1 and T2 are distributed randomly. Here, T1 bar and T2 bar are mean values of these hopping terms, and W is the width of the box distribution. This model has been extensively studied in the case that there is no randomness. This is because non-trivial topological phases emerge in this model. While I do not focus topological phases in this seminar, but this model is one of specific models in which topological edge states exist, which correspond to red lines in these figures. In addition, this model satisfies PT-symmetry, parity times symmetry, with this symmetry operator. PT-symmetry is related to the topic of this seminar. This model has entirely real bulk eigenmodes in a certain parameter region. The eigenvalues of bulk modes correspond to blue lines in these figures. And certainly they are real in this region. Such a real spectrum has been considered to be it has been considered that such real spectrum originates from such PT symmetry. However, in the next slide, I show that this eigenvalues can be entirely real without PT symmetry. These are symmetries of this model. This model satisfies chiral symmetry, particle hole symmetry, and time reversal symmetry with these symmetry relations. These symmetries are maintained also in disordered systems. As I clarify in the following, these symmetries plays crucial roles for the eigenvalue statistics in random systems. As I mentioned, this model has PT symmetry if there is no disorder. However, randomness easily breaks parity times symmetry since PT symmetry includes parity operation. As I mentioned, the real spectra of this model has been considered to originate from this PT symmetry. Therefore, it is naively expected that If a disorder exists, PT symmetry is broken, and then the complex spectra emerge. However, eigenvalues can be entirely real in this model without PT symmetry. These figures show numerically obtained eigenvalues when hopping terms are distributed randomly.
Can I ask a question about just in general about
please.
what you're discussing here?
Yeah, please.
You say that you can have a real spectrum without PT symmetry, but I don't know how you show that there isn't a P operator. I mean, the P operator doesn't have to be a reflection through the origin. The the P operator is any Hermitian operator whose square is 1. And to prove that there does not exist such an operator somewhere that has the property that P squared is 1, how do you even begin to show that? Can you show there simply does not exist any such operator? I mean, the P operator could be, for example, the P operator could be a reflection about the point 6, not about the origin. But it could also be much more complicated. It could be some sort of inversion operator. It could be almost anything. So how do you know that there does not exist PT symmetry? I mean, you have to, in order to show that, you have to show that there does not exist any such operator P.
Yeah, thank you for the comment. I cannot show that there is no such operator. But in this seminar, I say PT symmetry in a very, very narrow sense. That is, PT symmetry includes parity operation in such form.
Okay, so when you say PT symmetry, what you really mean is that P is a reflection operator through the origin. And that's what you mean by P.
Yeah, yes.
Okay, the reason I say this is because Qinghai Wang, for example, has published papers showing that there are all kinds of P symmetries that can arise once you know that the eigenvalues are real. It does not have to be a simple reflection operator.
Yes.
Can I
if we construct such P operator, the P operator depends on the, for example, the ensembles of random potential realization.
Okay.
But here, if I say PT symmetry, it means the PT symmetry operator which does not depend on the randomness realization. So I use PT symmetry very, very narrow, in a very, very narrow sense in this seminar.
Okay.
I think there's a stronger way to say it. The question is, does the system have some antilinear symmetry at all? I mean, what you're basically saying is the eigenvalues are all real. And so the immediate question is, does the system have some antilinear symmetry, not necessarily anything to do with parity?
Yes.
I mean, that's the sort of most general way to look at it. I mean, Carl and I would be very surprised, but we'll defer to you if you can actually establish that there is no antilinear symmetry at all. But that would be something to do with the disorder, not which may change. I mean, what I know about is for ordered systems. For disordered systems, there may be some escape clause. But in order to show that, you really have to show that there is no antilinear symmetry whatsoever. And that I don't think you've done.
Sorry, I do not understand.
Okay, well, we'll talk about it at the end.
Please continue, Ken.
Yes, thank you. Yeah, sorry. So I use PT sim. I use the word PT symmetry in this very narrow sense. And I want to say is that in this model, this PT symmetry was considered to the origin of the real spectra, but this is not true. But I do not state as a general. I do not state that there is no general PT symmetry, of course. So I continue. So in this model, eigenvalues can be entirely real without PT symmetry in narrow sense. In the left figure, the eigenvalues are entirely real. In such a case, as I mentioned in the following, statistical properties are determined from time reversal symmetry. In the left figure, the eigenvalues are real or imaginary, in which the parameters are different from the left figure. In such case, the statistical properties are determined from chiral symmetry, as I mentioned in the following. At first, I elucidate why eigenvalues can be entirely real in this model. This originates from the structure of the matrix. Please remember that in this model, a particle hops from A site to B site, or vice versa, from B site to A site. And such hopping terms are described by Hermitian Hamiltonian H0. And then in this basis, that is A sublattice and B sublattice, the H0 can be written in this off-diagonal form. Here, capital omega includes only hopping terms and does not include on-site imaginary potentials. The on-site imaginary potentials are included the anti-Hermitian term H gamma, and it can be written in this diagonal form with this basis. And then we can easily show that H square becomes H0 square minus gamma square. And then E square becomes E0 square minus gamma square. Here, E and E0 represent the eigenvalues of H and H0. And then
I'm sorry for the question. H and H0 don't commute.
sorry.
H and H0 don't commute.
H0 and
H don't commute.
So what? So what? H squared is what's written.
No, H squared is H0 squared minus gamma squared, but it does not follow that E squared is E0 squared minus gamma squared, because they're different eigenbases. I agree with you that operators H squared is H0 squared minus gamma squared.
No, but
I don't.
H squared commutes with H0 squared.
Well, that's what I asked. Does H commute with H0?
Yes, H0. Well,
Oh, okay, that's fine.
Ken, you can answer. Sorry.
That's what I asked. Thank you very much.
yeah, thank you, Joshua. It's okay. So E square becomes E0 square minus gamma square. So this equation means that if the minimum value of E0 square is larger than gamma square, then E becomes entirely real. And this is the motions of eigenvalues if gamma is increased. At first, if gamma equals 0, the eigenvalues are real, of course. Then the eigenvalue E can have energy gap around E equals 0. As gamma is increased, then this gap is narrowed. And after the gap is closed, then the eigenvalues go along the imaginary axis, like green arrows. In these cases, A and B, the eigenvalues are entirely real. And then the relation of pseudo-hermiticity is satisfied. This is because pseudo-hermiticity is a necessary and sufficient condition for the reality of eigenvalues. This relation means that the non-Hermitian Hamiltonian H can be mapped to a Hermitian Hamiltonian H tilde with the square root of eta. In this case, we can prove that the non-Hermitian Hamiltonian H and Hermitian Hamiltonian H tilde have the same symmetries. For example, if non-Hermitian Hamiltonian H satisfies this relation or this relation, that is, gamma H gamma inverse becomes minus H or minus H dagger, then we can show that gamma H tilde gamma inverse becomes minus H tilde with the same symmetry operator gamma. The other symmetries, the inheritance of other symmetries is in the same way. I give the proof of this symmetry inheritance in the next slide. We can read out two important things from this symmetry inheritance. First is that the ramified or increased symmetries in non-Hermitian systems shrink to one symmetry in regarding the Hermitian Hamiltonian H tilde. Therefore, the second sentence is reduced from the first sentence. That is, the eigenvalue statistics of H is determined from the universality classes in Hermitian systems, H tilde. This is because H tilde and H share the same symmetry, share the same eigenvalues because they are related by similarity transformation. So after giving the proof of this symmetry inheritance, I explore the statistical properties of H from this theoretical viewpoint. This is a proof. I consider the right eigenvalue equation and left eigenvalue equation of H, and consider the situation in which this bi-orthogonal normalization condition is satisfied. When all of eigenvalues are real, then pseudo-hermiticity is satisfied. Here we can take eta in this form. That is, eta is composed of.
Can I ask one question?
Yeah,
You are considering generic systems, not necessarily Lorentz invariant. Am I right?
Yeah, I consider generic systems with real eigenvalues.
Yeah, but they are not Lorentz invariant. So you do not have an underlying CPT symmetry, which would play the role of the linear symmetry that Mannheim and
I think CPT symmetry is not necessary in this discussion.
Yeah. I mean that's what would answer that. Yeah, if it would be the antilinear symmetry that Mannheim and Karl were having in there. Okay. Yeah, if they are not Lorentz invariants, then you don't have it necessarily.
Yeah, I think so.
That's the question. Don't worry. Thanks.
Yes, thank you.
To Nikos, any system which has relevance to the real world has to be the non-relativistic limit of a relativistic system.
Yeah, I would have thought. That's what I asked the question.
Therefore, you will have a CPT.
That's right. That's what I asked the question.
However, in this particular case, you're looking at a model which may not have a relativistic generalization. And
and that's what I asked the question.
Yes.
Indeed.
So then it's just a purely pedagogical. It's not. It can't apply to the real world.
Yeah, I mean, unless there is some system which
No, unless well, that's what we went back right to the beginning.
That's right.
If it is the non-relativistic limit of some relative system, there is a hidden antilinear symmetry.
Yeah, that's what I would have thought. But
Yes.
I find it hard to resist, but if Andreas promised not to chop time from Ken's talk, I will just make a comment. So Andreas, can I?
Go ahead.
Short, yeah. So this model, the SSH model, is a non-relativistic version, a lattice version of the Gros-Neve model. It's a 1+1 dimensional relativistic field theory of fermions.
But then there is a CPT symmetry, which is the antilinear symmetry, in my opinion.
Yeah, okay. Yeah.
Oh no, that's answering Philip's remark. That's
Well, not completely. It's a.
No.
It's a
I mean,
it's a disordered version of.
It's a disordered, yes.
Okay.
But in the
That
absence,
may change things.
in the absence of disorder, it is the
okay. In the absence of disorder, so in the
presence.
presence, but the presence of disorder would destroy completely the antilinear symmetry of CPT. Who knows?
Well, as Ken commented, earlier, if you would to define some alternative P operator, that alternative P operator, which is part of CPT, will depend on the realization of disorder. So it would change from realization to realization. So what's the use of it?
I just don't know whether it's relevant or not. But when you have disorder, sometimes in relativistic theories, you can put supersymmetric ways of putting in.
Yeah, and then it reduces dimensionality. Yes, maybe.
Yeah, but then you have the antilinear symmetry of CPT because supersymmetry has it. But anyhow, let's not interrupt further.
That's another seminar. Let's
let him
can continue, I think.
Yeah, sorry.
Sorry.
So I think that as Joshua-san said, such CPT symmetries depend on the random potential realization, if it exists. So I continue. We can take the positive definite operator eta in this form, that is based on the left eigenstates. Here I consider time reversal symmetry in this type. From this symmetry relation and eigenvalue equations, we can easily show that the left eigenstates are obtained from right eigenstates by operating T. Then we can show that eta inverse and eta are related by this relation with symmetry operator T, because eta and eta inverse are composed of left eigenstates and right eigenstates. And then at the same time, square root of eta and eta inverse satisfies the same relation. Then from this relation and original symmetry relation, we can show that H tilde satisfies time reversal symmetry with the same symmetry operator T from the original symmetry relation. In such a way, we can show that the symmetries of non-Hermitian Hamiltonian H is inherited to the Hermitian Hamiltonian H tilde in the same way for other symmetries. As I mentioned, from this symmetry inheritance, the statistical properties of H can be determined from the universality classes in Hermitian systems, H tilde. Therefore, let me remind the universality in Hermitian system here again. So in random Hermitian systems, there are typically two phases, insulating phase and metallic phase. These phases are discerned by the the eigenstates are localized or extended. In the insulating phase, the level spacing distribution becomes Poisson distribution because eigenvalues are independently distributed. On the other hand, in the metallic phase, since extended eigenstates exhibit level repulsion, then P of S obeys such functional form. The blue and red and green lines are determined by the universality classes, or equivalently, the existence or absence of time reversal symmetry and the value of square of T. From the discussion above, we can understand that such such classification or universality classes should be inherited from non-Hermitian systems to Hermitian systems. This is because the symmetries of non-Hermitian Hamiltonians are inherited to Hermitian Hamiltonians if eigenvalues are real. In order to confirm this this feature, we numerically calculated the localization length in the non-Hermitian SSH model. Sorry, I forgot one slide, sorry. These are the symmetries of the present model, non-Hermitian SSH model. Please remember that the non-Hermitian SSH model has chiral symmetry, particle hole symmetry, and time reversal symmetry. As I mentioned in the previous slide, time reversal symmetry determines the universality classes for level spacing distribution if the corresponding eigenstates are delocalized or extended. So in order to focus on extended states, we calculated the localization length of the eigenstates. First, please note that in this model, there is not extended states in the thermodynamic limit. However, in finite systems, if the localization length is large, such eigenstates can be regarded as extended states. So we calculated the localization length from the inverse participation ratio and take the eigenstates in this range. That is, the localization length is above a threshold value. In this range of eigenvalues, the eigenstates can be regarded as extended states, which can be understood from this figure. Out of this range, eigenstates are localized, like in this figure. Focusing on only on such extended states, we calculated the level spacing distribution in the non-Hermitian SSH model. In this figure, the green dots represent the numerically obtained P of S. And in the inset, the green, blue line represents P of S equal S. And then from the inset, we can understand that the P of S grows linearly near S equals 0. Which is one of the main features of Gaussian orthogonal ensemble. Also, in this figure, red dashed line represents the P of S in the Gaussian orthogonal ensemble. Since numerical results and theoretical expectation agree well, we can conclude that P of S in the non-Hermitian SSH model obeys that of Gaussian orthogonal ensemble in Hermitian systems. This is because the non-Hermitian Hamiltonian can be mapped to Hermitian Hamiltonian H tilde, and the symmetries of H are inherited to H tilde. In other words, H tilde is a real symmetric matrix in this model. And this is one of main results of our paper. Next, I shift to the case in which imaginary eigenvalues exist. If imaginary eigenvalues exist, then the symmetry inheritance cannot be utilized because H cannot be mapped to Hermitian Hamiltonian. These are numerically obtained density of states if imaginary eigenvalues exist. The density of states along real axis or imaginary axis. Please remember that in this model, eigenvalues are real or imaginary. There are two interesting features in these figures. One is that the density of states diverges along the imaginary axis. Also, the density of states vanishes at the origin, E equals 0. I elucidate the origin of such features in the following. The first feature, that is, the divergence of density of states originates from the Dyson singularity. Please remember that the eigenvalues of H are determined from the eigenvalues of Hermitian Hamiltonian H0, obeying this relation. Also, it is quite important that this Hermitian Hamiltonian satisfies chiral symmetry in this form. Here, please remember that in chiral symmetric one-dimensional random systems, the density of states diverges at E0 equals 0. And this singularity is referred to as Dyson singularity. Then the density of states for H0, written as rho tilde E0 here, should diverge obeying Dyson singularity at E0 equals 0. Here, rho E is the density of states for the non-Hermitian Hamiltonian H. And the density of states determined from the density of states in Hermitian systems following this relation. Also, the E0 equals 0 corresponds to the E equal plus minus I gamma, which we can understand by this relation. Then rho E should diverge at E equal plus minus I gamma, originating from Dyson singularity. In this figure, green dots represent the numerical results, and red dashed line is a fitting curve based on the functional form of the Dyson singularity. They agree well, and we can conclude that the divergence is originate from Dyson singularity. At last, I explain why density of states vanishes at the origin. And this can also be understood from this relation. From this relation, we can derive the behavior of rho E near E equals 0 in this form. From this equation, we can understand that rho E drops linearly towards E0 equals 0. Sorry, E equals 0. In these figures, the blue dashed line represents the density of states obeying this functional form. And the numerical results and analytical expectation agree well. This is a summary. In this seminar, I talked about the non-Hermitian SSH model and clarified that eigenvalues can be entirely real without PT-symmetry. Note that PT-symmetry is a very narrow sense in here. I also showed that if eigenvalues are entirely real, the non-Hermitian Hamiltonian can be mapped to Hermitian Hamiltonian, and they share same symmetries. Originating from this symmetry inheritance, we confirmed that the level spacing distribution of this non-Hermitian SSH model obeys that of Gaussian orthogonal ensemble. I also showed that if imaginary eigenvalues exist, then Dyson singularity emerge in this model, whose origins are chiral symmetry. Thank you for kind introduction.
Thank you very much. Any more questions or comments?
Thank you very much, Ken.
I have a comment on the symmetry, actually, since this featured quite a lot. Yeah. So there are papers, and I have written some of them, on spin models where you don't think of parity as reflecting the whole chain. Yeah. The parity operator can act locally, meaning you just do something to individual sides. Yeah. So for instance, you can define P as the tensor product of all sigma z operators. So in the Ising model, if you perturb it, you add a nonlinear term, you can use that. That has been shown. And then you just flip some of the spins. So sigma x goes to minus sigma x, and sigma y goes to minus sigma y. So, but locally, you're not reflecting the entire chain. And that symmetry governs the reality of the eigenvalues, just as a comment.
This is sort of a gauged parity?
No, it's not a gauge. Yeah. You just, as has been said several times now, you need an operator that p squared is 1. Yeah. And then you add your antilinear part, and then you have built up your PT operator. Yeah. But it depends on the XXZ chain. You have to think globally, but on this change, you have to construct it individually. Yeah, on each side. Yeah, but you have to act on each side, of course. Yeah, but you're not reflecting the entire chain. Yeah, and we have shown these symmetries govern the reality of the spectrum. Yeah, how you trace that back to the field theory, I wouldn't know. I don't think this is manageable. Yeah, there was the comment by Nick about the CPT. Yeah, I don't think this local symmetry can be traced back in that sense. Yeah,
yeah, but I think this. Sorry, Ken, maybe you want to answer.
Yeah.
It's just a comment. Yeah.
Yeah, thank you for the comment.
Well, I think it falls under what Ken already mentioned, that even if you could find such a P operator, alternative P operator, it would change from realization to realization because the potential changes in each realization. So
well, I mean, that's the nature of the game. If you change the potential, the P symmetry might change naturally.
Yeah. Okay.
Yeah.
So, yeah. So it's case dependent, unlike.
Well, that's not surprising that the P symmetry is potential dependent, no?
Right.
I don't think
I agree.
that's not surprising. Yeah.
But the question is whether you can do it for each realization. So if you can prove that there is no realization for which you cannot find such a locally varying alternative.
Yeah, but as Carl said, not finding it doesn't mean it doesn't exist. Yeah.
Right. And everybody
it's just you have to look in a different way. You shouldn't look at it globally. You should look at it locally. Yeah.
Can I just make a very brief remark about that?
Yes.
The point is that you have on one hand a CPT theorem, which is a rigorous theorem that you prove, and you prove it on the basis of general features of a quantum field theory. Namely, you have to have relativistic invariance, and you have to have a Hamiltonian that has real eigenvalues and has a positive spectrum. Okay, very fundamental properties. And you establish a CPT theorem, and buried in that is the issue of parity and time reversal and so on, which is all related to the Lorentz group. Here, it's sort of in the reverse, okay? We are told that the Hamiltonian has a positive spectrum, and the question is, do you have a PT symmetry? And this is not, it is not generally known, although there have been a lot of investigations, at least at the matrix Hamiltonian level. Okay, and as I said before, Qinghai Wang wrote a paper on this where he investigated matrices of given dimension. And if you know that their eigenvalues are real, is there a P operator, which is a matrix whose square is 1, such that that Hamiltonian commutes with PT, where T is simply complex conjugation? And the answer appears to be there always exists a parity matrix, which is an n by n matrix, such that and it's Hermitian, such that P times T, which is complex conjugation, commutes with that matrix. Okay,
And
that's the generic issue.
And I believe here, Carl, because in Ken's problem, the eigenvalues are either real or purely imaginary, you can define such a complex conjugate would exchange these eigenvalues.
Uh-huh.
I believe there is some, there must be some antilinear, but I don't know. It might be a good exception. I believe there must be something underlying the construction.
The main point is this, although this has been investigated in great depth in the case of n by n matrices, when you go to theories with an infinite number, infinite dimensional matrices or a continuum theory, that has still not been proved, and it's an open question. And it's a very difficult question because proving that something doesn't exist is very difficult.
Yeah, all you want to say is that there is no no-go theorem that prevents you from constructing a PT symmetry of some P, of some projection, I guess.
Right.
I mean, I don't know. I'm not. I mean, it might be an interesting counterexample what Ken is presenting. Honestly, it could be. I don't know.
Can I add something? No?
Ali broke up.
Yes. Well, the precise statement is that if the Hamiltonian has bi-orthonormal systems, then there is always an antilinear symmetry. This I proved in 2002. And finite dimensions always satisfies this condition. So the only thing that will not satisfy it is when you have a Hamiltonian operator, it's a linear operator, whose eigenvectors do not give you a bi-orthonormal system. So in that case, there are counterexamples.
No, but here it's the good case. Here you always have a base bi-orthogonal.
Well, if in finite dimensions, you always have bi-orthonormal systems.
And therefore, as Ken mentioned, you can generate the eta matrix from the right eigenvectors and the inverse from the left eigenvectors, or the other way around. Yeah, exactly. Like
Antilinear symmetries do not require reality of the spectrum. So if it is pseudo-Hermitian by not positive definite operators, still you do have antilinear symmetry, and this can be proven in the most general case.
If I may comment, well, let me comment on this point. The question of the CPT theorem when the Hamiltonian is not Hermitian or when the eigenvalues are not real is something I did investigate. And the theorem that I proved was you still have a CPT theorem if two things happen. One is you have probability conservation, which you do. And the other is that you have complex Lorentz invariants, not real Lorentz invariants. You have to have the proper Lorentz group, not the restricted Lorentz group. Now, I don't know whether your model, when it's made relativistic, would have complex Lorentz invariants, even if it did have real Lorentz invariants. So there may be an escape clause, but generally you should expect that you do have an antilinear symmetry. And it's even true if the eigenvalues are not real, even if they're complex, as long as you have this complex Lorentz invariance and probability conservation. Now, something I wanted to ask, and I'm with friends, so I hope I'm not saying something totally stupid. But if you go back to the two Hamiltonians, the H0 and the H gamma, if you could put them back up. Yeah, yeah. I just calculated the commutator and I found that they didn't commute.
What?
I found that they anti-commute.
What?
Yes, you could, because you can write H0 as sigma plus omega sigma plus omega dagger sigma minus, and sigma plus doesn't commute with sigma 3.
Yeah, yes, H0 and H gamma are anti-commute in this
They
case.
anti-commute. So how can you say that E squared is E0 squared minus gamma squared?
But
Yes.
H gamma commutes with H0 squared.
H0 squared commutes.
Yes,
with
that's
H gamma.
excellent.
Ah,
Excellent.
Yes, yes.
okay. All right. H0 squared commutes with H.
And in fact, the fact that H not anti-commutes with H gamma, that's the chiral symmetry. That's why the spectrum
Yes.
of H naught comes with plus minus pairs. Of eigenvalues.
That's what I asked at the beginning. And
Oh, okay. No, but I thought you asked whether H square was commuting with H naught square.
I probably said it that way, but I actually calculated the commutator of H0 with H gamma and it wasn't 0. Okay, that answers that. Yeah. Okay. Anyway, that's my first. That was my main concern. Okay. But I think what you have to be very careful here is, and Ali pointed it out as well, you do have an intertwining operator. You do have an H dagger is eta H, eta to minus 1.
When the spectrum is real.
Yes, that's right.
Is real.
Yes.
That's when gamma is not too big, too large.
Sorry,
When gamma is not too large, I mean the spectrum.
Wait a minute, but what is eta? Haven't you constructed eta?
Well, Ken showed it out of the.
Well, please show it again. I'm a little bit slow.
Which slide?
No, the eta matrix. You constructed it out. Yeah, this one. Look in the middle line. Look in the middle line.
Yeah.
So you construct well implicitly in terms of the.
Okay, so if I take your eta and I just calculate eta H eta minus 1, you tell me, do I not get H dagger? If gamma, I mean, what happens if gamma is less than, if E0 squared is less than gamma squared? What does eta do to H?
Well, Ken, do you want to take it? Do you want to answer?
Sorry,
Now I've got the eta and I've got the eta to minus 1, and I apply eta H eta minus 1. What do I get?
No, when gamma becomes too large, you start encountering exceptional points, and that.
I'm past the exceptional point. I've got gamma squared is greater than E0 squared. What does eta do to H?
It doesn't give you H dagger because the eigenvalues are no longer real.
No. I know it doesn't give H dagger. I'm asking what it does give.
Well, I'm not sure you have all. I'm not sure you have all the eigenvectors in that case.
Of course I have. If the energies are complex, I mean, if I'm not at an exceptional point, the eigenvectors are complete.
Well, when gamma goes to infinity, very large compared to the disorder, so I can neglect the disorder. Then H is essentially H gamma, and I agree that that is diagonalized. It's anti-Hermitian and therefore diagonalizable. And
its eigenvalues are in a complex conjugate pair, and it has a PT symmetry. It has an antilinear symmetry
in the broken phase, because the eigenvalues are imaginary.
We were saying all along that whether you identified it or not, your system has an antilinear symmetry. And now you've given me an example where you let gamma go to infinity and it's self-evident, because you just get I times sigma 3 and the eigenvalues are in
we never claimed it doesn't have. We just said.
But you did. That was your big result. You said, look, we can get real eigenvalues without a PT symmetry. And Carl and I objected. We said you must have some other antilinear symmetry. And now you've given me an example. You said gamma going to infinity.
No, gamma going to infinity is not a disordered Hamiltonian. The objection was that when disorder dominates, whatever you can define as a P operator will depend on the realization of disorder. And as Andreas kindly mentioned his example for spin chain, which is kind of similar, then the P operator may be defined pointwise on the lattice.
Then I'll ask my question again. What does eta do to H when gamma is not infinite and when you do have disorder? That was my question originally. You said, well, if gamma goes to infinity, I don't have to worry. I understand that, but now will that gamma not be infinite? So all I'm asking is, how does H transform?
You mean when you have both real and imaginary eigenvalues? When it's
yes, when you have a complex conjugate pair of eigenvalues, there may be the question that's really asking: is there some other eta, not the one you've constructed for the real eigenvalues, which still sends H to H vector? And
do you ask about in which case?
The question we've been asking all along, namely, does the system have some other antilinear symmetry?
The speaker would like to speak. Can speak? Go, please.
Yeah. I don't understand the question. Do you ask about in which case in this figure? I don't understand.
I'm sorry. Do I ask about?
Do you ask about which case?
Case F.
F. Yes. F. No. I think. Okay. F case. Okay.
F is
okay.
fine.
Okay.
Case.
Okay. In F case, I think that the eta can be constructed in the same way. This slide.
Okay.
This is because the Hamiltonian, although the eigenvalues are not entirely real, but IH have entirely real eigenvalue in this case.
Yes, but
you cannot do that.
So in such a case,
is explicitly Hermitian in your construction.
Yes, the eta is going to be not n, but it's going to be n for imaginary plus ket times n for imaginary minus fra. It's going to be overlap.
You cannot be.
That will be the eta in this.
May I add a brief comment on this? All your system remains self-adjoint in the grind space, whether you have exceptional point or not. So all the grind space picture is preserved, this PT symmetry underlying, as Andreas told, Carl told, and so on. The point is actually what's happening here is when you can imagine it very simply. Away from the exceptional point, your Hamiltonian is diagonalizable. And this means that you always have two blocks of complex conjugate eigenvalues, something with one side of the imaginary part, the other the opposite side. And so you have a combination instead of diagonal eta in a certain sense, you have always pairwise flipped symmetry therein. And it is happening at the exceptional point. You're going from one structure to such a pairwise flipping. You have a pairing between those complex conjugate eigenvalues, left and right. That's all what's happening.
Okay, very good. So Uwe is saying if you're in the region where gamma is greater than E0, the energies come in complex conjugate pairs, the eigenvalues, eigenvectors are complete. You can diagonalize the Hamiltonian into blocks of opposite complex conjugate eigenvalues.
Exactly.
And that Hamiltonian has an antilinear symmetry, and
of course.
therefore you can transform back to the original basis, and you'll have some different antilinear symmetry.
Yeah, sure.
Yeah, but
it's even at the exceptional point. The symmetry, the global symmetry is always the same. It's only it's locally broken or not broken.
Even survives at the exceptional point. Yes.
Yes.
But Philip, if you have case F, you have purely imaginary eigenvalues. Isn't it like this that if a Hamiltonian has purely imaginary eigenvalues, then I times the Hamiltonian is Hermitian or PT-symmetric. So in a sense, the Hamiltonian gets anti-Hermitian. So you have a certain equivalence for the product of I times the Hamiltonian.
Well, yeah, the metric. What I'm saying is that I sigma 3 has an antilinear symmetry. That's all I'm saying. I don't think that's in dispute.
No, all the symmetry is remaining. It's PT symmetry. All the problem, independently of the concrete eigenvalues, it's remaining a self-adjoint in a grind space. And then you have these different sectors with phase transitions between the sectors. That's all what's happening. You have simply restructuring of the eigenvalue and eigenvector structure. That's all. But the PT symmetry of the operator itself, it remains.
Yes. Well, the antilinear symmetry.
Yes, the antilinear symmetry. Yes.
There must be something there. I mean, there must.
It's elementary.
Case F or case E.
What I don't understand, I mean, we discussed this 20 years ago.
Yeah, sure.
Exactly.
I mean, this is going on and on and on. Please read the papers published in 2000 and 2005.
Sure, exactly.
No, I think that
it's only very special realization, nothing else.
Yes, I think that most of us here are of the opinion that there is an antilinear symmetry.
Yeah, I mean, in this, sorry for insisting, but I believe there must be. A disorder can be described as a fermionic system, all right, through some replica effects or whatever. So aren't these fermions obeying a complex Lorentz transformation in some limit, which implies an antilinear symmetry? Of some form, not of the ordinary reflection symmetry about the origin, of course not. So I would have thought, I mean, I would like to see the Hamiltonian actually.
Yeah, he wrote Hamiltonian explicitly.
Yeah, but can I see it, please?
Yes. You have the very simple intuitive picture. You are just going through a black hole horizon. That's the same situation. Outside you have one metric, inside the horizon you have a different with opposite sign. It's the same effect, nothing else.
So is there an antilinear symmetry or not?
Well, Nikos, we're all in agreement that there is, but
that's what I'm trying to understand.
To Ken and Joshua, they haven't given us a proof that there isn't, and
we don't try. We didn't claim there wasn't.
No, but when you
never claimed it.
When you said that you can get real eigenvalues without PT symmetry.
Well, he meant
without that.
I'm sorry. Ken said that he meant PT in the restricted sense.
Yes, and that's what we have to. We understand that, but we all asked you.
Can you show me the Hamiltonian, please? I just try to. Can you show me the transparency of the Hamiltonian? Where is it? The explicit one, please.
Now that's a picture. Can you show the?
You're not a picture. I want to see.
Yes.
Here. Well, yeah. This is what. I mean, in terms of fields, this is written in terms of states. So in terms of fields, the disorder must be described by fermions. All right. So
No,
does this?
What fermions? There are no fermions here.
Well, there are in disorder systems. In the 1+1 disorder systems that I know, I think there are.
Okay,
fermions.
okay. These are words. These are words. This is a tight binding matrix. Well, please, here it's written. It's if you want to write it in terms of.
But is it a matrix model or what?
No. Well, it is a finite system, and therefore a discrete finite system, and therefore it's a matrix.
That's the system with the omega dagger.
Yeah, well, in another basis, omega dagger in another basis. This is in the lattice basis. This is written in the hopping. This is the hopping Hamiltonian. The omega dagger representation is the chiral block representation.
Yeah,
it's
that's
non-local in space. So you have a particle hopping along the x-axis. So the lattice points are x-1, x +1, etc. And you are hopping from one unit cell to the other. From one block, from one unit cell to the other, you can hop with amplitude T2. And within each unit cell, between the A and B two sublattices.
Yeah, but you said that this, in some limits, reproduces the Grosnevet, which has fermions.
Yes, it reproduces.
Okay, so my question is, does this exhibit a complex Lorentz transformation in the presence of disorder? This is my question as an ignorant. Does it?
Well,
because if it does, then there is an antilinear.
If you write the continuum limit of these.
Yeah, the continuum limit, indeed.
Okay, I mean, ignore the I gamma, ignore the non-Hermitian part. Just look at the disordered Hermitian part.
Yes.
What you will get a Dirac fermion coupled.
Perfect. That's exactly what I was saying.
Let me finish. Let me finish. You will get a Dirac particle coupled to a random U1 field.
Yeah, that's fine. I'm sorry. That's what I was saying. These are fermions, all right? In 1+1. Whatever the spin means.
But the disorder has nothing to do with the fermion. The disorder is the gauge field.
Yeah, that's right. But still, is this limit and the CPT invariant in some generalized sense formalism? I believe there must be.
Well, it should be invariant under the complex Lorentz group.
Look, it's like asking whether QED in some fixed background is CPT invariant. If I fix the background, if I look at a fixed background, of course, the parent theory is CPT invariant, but I study it in a given background.
Yes,
in a given gauge field.
Yeah.
So,
okay. Can you show us again the Hamiltonian with the omega and the omega dagger?
Can you show him?
Yes.
Hamiltonian.
In omega dagger, in the omega dagger picture. Yeah.
Okay, now then, that Hamiltonian.
It's another
omega depends on the disorder.
Omega,
yes.
Omega is an n by n block, and this n by n block is lower triangular matrix. It's a very sparse matrix with hopping only in one direction. Okay. The hopping is different from link to link.
Okay. Now, if we were to go back to the limit of T1 and T2 being ordered,
yes, okay,
then you could find an antilinear symmetry for H0 plus H gamma.
Yes.
So what happens?
Actually, it's known. Ken, I think we even cite it. Some people wrote it down.
Yes, because what the question is, what happens to that antilinear symmetry when you introduce disorder? Because you don't change the
it gets screwed up. It's screwed up. It doesn't work anymore because it depends on the translational invariance of the system. So maybe some strategy like what Andreas mentioned, where you define the P operator pointwise, maybe that would work, and that's what we supposed would happen. But then, as we argued, that would change from realization to realization. So what's the use? I mean, physically, practically, what do you make of it? It's useless if it changes from. It's lost over the average. When you average over all realization of disorder.
It's not useless for one particular realization. You can see how it governs the reality of the eigenvalues.
Yeah, but we are interested in statistics.
I understand. Yeah. but
for
that's
us,
what
it doesn't
happens.
work. Yeah.
That's what happens.
Yeah. So we cannot use it practically.
No, I'm not sure. Because you have this underlying symmetry, it's remaining. The statistic will change, so you will have a very nice association of this underlying symmetry changes to your statistics.
Okay.
So
Okay, but
it's
symmetry
contrary.
can-
It's even more interesting.
It's not a symmetry of the ensemble; it's a symmetry of case by case. So.
But it's mathematically it's irrelevant.
No, that's I agree. That what gives the spectrum. That's what renders the spectrum real or purely imaginary or on the cross shape. But that's the underlying deep reason. But we were calculating averages, average spectra. So it's washed out when you average. All this realization of the P operator, whatever it is, it's washed out.
Yeah, but you first have to find it to say what happens to it. Yeah.
Yeah, I suppose you can. Presumably, if one think hard enough along your suggestion, you can probably prove that it exists realization by realization.
No, it's proven that it exists. That's a fact. You just have to identify it.
Right. I mean, the mere fact that we have the similarity transformation means that it must exist. I agree.
So let me ask again the question. Is there an underlying linear symmetry that leads to an understanding of an underlinear symmetry leads to an understanding of the real eigenvalues? Even if there is no this specific PT, because as Ken said, this is in a narrow session. So should I understand that there must be this symmetry or case by case?
Well, that's what we just said, that it must be somewhere in the background. Yeah. But it's not of very practical use. I mean, it's just responsible to the reality of the spectrum.
That's right.
It's much easier to see that the spectrum must be real if gamma is not too large from this simple relation, h squared equals h squared naught minus gamma squared. It's easier to see it from there.
So then this with agreement with what Philip and Carl were saying in the beginning, that the PT-symmetry requires a reality of eigenvalues requires some at a certain level.
Yeah, but we never said it doesn't exist here. It's just not of very good use.
Okay, but yeah, I'm not asking the use. I mean, but just for an understanding, that's all I was asking. That's all. Yeah. Okay.
Should we stop this discussion here? Ken, do you
I've just got one more question. In this H0, the omega in the top left corner, in the top right corner, depends on a particular set of coordinates.
Say it again.
The omega in the top right corner of H0
is
a hopping operator between x and x plus 1.
It's a Dirac operator, if you like. A Dirac gauge.
What about the speaker answer?
I don't like, I'm asking, it seems to me that omega relates x to x plus 1, and omega dagger relates x to x minus 1.
Right.
Yes.
So I'm not sure that this H0 is Hermitian, because the omegas and the omega daggers are operating in different spaces. It's not just a 2x2 matrix.
Who said a 2x2 matrix?
Ken wants to answer this question. Ken, would you like to answer?
The omega is the sum of x and x prime, and then these becomes Hermitian.
Well, what basis are you calculating H0 in?
Sorry, H0n, H0x?
What?
Sorry, sorry, I don't understand your comment. But please explain.
Well, anyway, I'm sure you got it right. I just don't see it. It's all right.
No, but he didn't understand your question.
Well, I'm asking, how do you write omega dagger? You just think you conjugate this equation here, that you've got x omega x prime?
Yeah.
And then what happens to T1 and T2? Are they real?
T1 and T2
are they are real. Yeah, they are real.
They're to be real. Okay.
Yeah, T1 and T2 are real here. And the H omega dagger is just a transpose of omega.
Yeah, no, you see, what I'm asking is this. The omega between x and x prime depends on x and x prime plus 1.
No, 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 no.
No, you've got it written down there, delta x,
No,
x
no,
prime.
you have T1x and T2x. So
No, you've got written down there, delta x, comma, x prime plus 1.
right.
This means that
omega dagger would have a delta x, x prime minus 1.
Yes.
But that's not the conjugate of this quantity. You see, your omega has a delta of x, comma, x prime plus 1. Your omega dagger will have a delta of x and x prime minus 1. And that's not the Hermitian conjugate.
What it does, it annihilates a particle at x prime plus 1 and shifts it to x, and that goes left. I mean counterclockwise, right?
Yeah.
That's the T2. That's from unit cell to unit cell, and T1 is within the same unit cell. T1 maps between A and B sublattices in the same unit cell.
Now, T1 I'm not worried about. I'm worried about T2 and its Hermitian conjugate.
Look, Philip, it's very simple. Just imagine a particle hopping on a ring. Okay, it's a periodic boundary condition. So it's a particle.
Okay, yes, because you're going to close the chain.
Yeah. So
Okay.
omega is counterclockwise and omega dagger is the clockwise.
Okay, yes.
That's it.
I think you can also see it by expressing T1 and T2 as functions of x prime. Both of them are functions of x prime.
Yes.
T2 is not the function of x prime. So
yes,
this term only takes finite value when x and x prime are nearest neighbor. And
but
T2 is
minus
only the
x prime.
Yeah.
Okay.
Okay, Ken, you have the last word. You want to say anything to all the comments you have received?
Yeah, so let me summarize. Here, in this model, the PT symmetry in very narrow sense is absent, but in more general sense, PT symmetry exists, of course. But such PT symmetry depends on the random realizations. So this is a critical difference between the PT symmetry, in this form, and the PT symmetry in more general sense. So I want to say is that PT symmetry in this form is absent, but I don't say that PT symmetry in general form is absent. I don't say that the PT symmetry is absent in general form. But I want to say that such more global symmetries are inherited from H to H children if eigenvalues are entirely real. So what I want to say is such symmetry inheritance in this seminar. So thank you for the discussion.
Thank you very much.
Thank you very much, Ken.
Let's all thank Ken again. Thank you.
Ken, very
Thank
nice.
you, Ken.
Thank you.
Ken,
Thank
may we ask you a